Hey there, Mustangs. Welcome back to another edition of No Hair, No Problem. Like my new cuffs hat I got here. Um, so, quick story for you guys. I accidentally lost my wife's audiobook. Now I'll never hear the end of it. All right. Anyways, in this lesson, we're going to be working on inverse functions. And inverse functions are important because they allow us to solve for functions. Just like when you think about adding, the inverse of adding is subtracting, multiplying, the inverse of multiplying is dividing, and so on and so forth. There's multiple different inverse operations that exist in mathematics. Functions, we use inverse operations to solve them as well. And it allows us to do some higher level math stuff. So without further ado, let's get started here. So what you're going to learn is that you're going to find inverse functions in formula and you're going to verify them. You're going to use graphs of functions to decide whether functions have an inverse function. And then you're going to determine whether functions are one-to-one. And then you're going to find inverse functions algebraically. That's probably going to be the hardest part, is finding them algebraically. Okay? So the existence... a function exists if the graph passes. We've talked about this rule before. It's called the vertical line test. Line test. And we call it the VLT. So a function exists, if you recall, as long as the graph is touching only one point throughout the picture. So when we look at this right here, we've got a line where it touches only once, only touches once, only touches once, so on and so forth. Everywhere in the graph, a vertical line is only touching my graph once. So that makes this a function, okay? And then if you recall, an example of something where it's not a function is when we have maybe like a y squared is equal to x. So because the y is being squared, what ends up happening is we get a graph that looks like this. That's the positive and the negative of the square root of y. And so if I went ahead and drew in a vertical line here, you could see it hits more than one point, so this is not a function, okay? So a function has an inverse function if its graph passes and now this test is called the horizontal line test. Okay, and we'll call that the HLT. So for a function is what we call a one-to-one if it passes both the horizontal and the vertical line test. So what does this look like? Well, let's take a look at some problems here and we'll kind of assess if this is in fact the case. So when we look at the existence of an inverse function, from its graph, it is easy to tell whether a function of x is one-to-one. Simply check to see that every horizontal line intersects the graph of the function at most once. So this is called the horizontal line test. So when we look at this, we're looking at this horizontal line. You can see that it actually hits two separate points there, okay? Just for the heck of it, let's look at the domain for this, because this is going to be a really big part when we talk about the domain and the range of these, okay? The domain for this graph, you can see that this is going to the left forever and it's going to the right forever. That's because the graph is going up and it's going up here. Okay, so the domain is that it goes to negative infinity to positive infinity. And for the range, when we're looking at the highest point to the lowest point is right here, which is at 0, and the highest point, it goes up forever, okay? So again, when we look to the side, we're looking left, we're looking right, and you can see it goes to left and right forever. And then when we're looking up, it goes up forever, but as far as going down, it doesn't go down forever. It actually stops right here, okay? All right, let's go ahead and take a look at the graph of an inverse function, okay? So the graph of a function and its inverse, f of negative 1, so f of negative 1 from here on out we'll call inverse of function, are related to each other in the following way. So that if you're given points A and B and they lie on the graph of f, then the point BA must also lie on the graph of the inverse and vice versa. So what this means is that the graph of the inverse is a reflection of the graph of f in the line y is equal to x, as shown in figure 1.39. Here's what happened here. When we take the A and the B, you can see that we swap them and we end up with B and A. Well, when we say A and B, we're really saying X and Y. And so if I just take the X and Y and I switch their places, that should give me the inverse. So you can see right here, X and Y are just swapped. So what does that mean? Well, that means that if I look at the graph of any point, it's going to reflect over this line right here. So for example, let's say I look at a point right here and I put it at 3, 2, and I was to go ahead and flip those two numbers, I would have 2, 3, and you would see there was an exact reflection directly over, so it literally just reflected up and over this equation, y is equal to x. Okay, so that's what the inverse is going to look like. So verify that the function f and are inverse functions of each other. Well, let's take a look at our picture. Okay, you can see clearly that when we look at our picture here, this is the equation y is equal to x, and we can see that this line right here, if I was to take that and go ahead and reflect it over, it ends up equaling this exact line. Now, how do we check this? So the way that we look at it is, let's just look at a point that's on our graph. So for example, if we look at one of the points that's on here, you can see we've got a point at 2, 1. So there's a point right here at 2, 1. If it is in fact an inverse of it, I should see the reflection over the y is equal to x, meaning I switch the x and the y, and we should see that point. So the reflection of this would be at 1, 2. And if I go to 1, 2, you'll see that right there. So here's 1, 2. You'll see that right there, there's that other point that's reflected over, and this is in fact a reflection over y is equal to x. So these are in fact inverses of each other. Now here's what I want you to notice. Okay, and this is the important part. I'm going to actually flip over to decimals here in a second for this. When we look at this function, it's important that you recognize the domain and the range for this. So when we look at the domain of this first function, that's the red one that we see right there. Let me highlight it there for you. Oops. When we look at the red function right here, okay, look at how this graph moves as it moves left to right. The end behavior of this graph right here is going down, but it's also going to the left. And the end behavior of this graph right here is going up, but it's also going to the right. And remember that when we're talking about the domain, we only care about the left and right behavior. So you can see that in this case, this graph is going to the left forever, and it's going to the right forever. So negative infinity to positive infinity. Okay? When we look at the range of this, we're talking about the up and the down direction now. So in this case, it's going up forever and it's going down forever. And so the range for this is going to be negative infinity to positive infinity. Okay. When we look at the domain and range of the second function, this one right here, here's the deal. I'm not even going to look at this one in the picture. We'll confirm it in a second, but here's what happens. When we talk about inverse functions, we said that we can take the x and the y and switch them. Well, that is exactly what we do when we take the domain and range of the functions. We're going to swap their places. That means that when I look at the domain and the range of my new function over here, my domain is going to be negative infinity to infinity, and my range is going to be negative infinity to infinity as well, because that's just swapping the domain and the range from my original function. And you can tell that this is actually what happens, that my graph goes to the right and it goes up, and it goes to the left and it goes down. Okay, and the domain is that it goes left and right forever, and you can see the range is that it goes up and down forever. All right. So let's take a look at this one here. We have to know that a function could be represented by a set of ordered pairs. Okay. And so if a function f of x has a domain, again, that word domain is another way of saying x values, consisting of the set 1, 2, 3, 4, and a range with the set of 5, 6, range is again y values, with the set of 5, 6, 7, and 8. Again, this is y values. Identify the domain and range of the inverse. So this is just practicing doing what we just talked about, how when we take the x and f of x, we are being given the points 1, 2, 3, 4, and then we're given the values 5, 6, 7, and 8. And if I said, let's go ahead and find the inverse of this, you're literally going to take your points and just swap their places. So that 1 and the 5 will swap. And what's going to happen is all of these points right here, we'll duplicate them, are going to now swap, and they're going to actually move over here. So it's going to be right here. And that these points right here will duplicate and are going to end up over here. So all we did was just take the x's and the y's and we just swapped their places. And so when we look at the domain and the range, we talk about the domain and the range switching. The domain in this first one, sorry, let me rewrite this. The domain in this first one is 1, 2, 3, 4. Okay. And the range in this one is 5, 6, 7, 8. Okay. And then when we look at the new function, the inverse function, which, hang on, I got to change this. My apologies. This is supposed to say f of -1, x, not y, sorry. You can see that what ends up happening is the domain and the range just go ahead and swap places. That now this value right here, we're going to duplicate that, is my domain. You can see that's my domain now. And the range, let's go ahead and copy that, is over here now, and that's now our range. So that you can see that they actually swapped places. Okay, this is how we find the inverse. You take the x and y and just swap them. All right? So how do we find inverses when we're doing them algebraically? Okay, what we do algebraically is, this is where we learned about in 1.5, we talk about composition functions and taking one function and putting them into the other. So the rule is that if I take my second function and I put it into my first function and I simplify it, I should end up with x for the answer. And if I take the first function and I put it into the second function and simplify it, it should end up equaling the other, or it should end up equaling x. So we call this a biconditional, okay? It both must be true. Okay, this is a biconditional statement that one has to be true and the other one also has to be true. So when we're doing this, you have to prove both of them are in fact true. So when we look at something like this and we say, let's solve it algebraically. We'll do a proof in a second, but when we say solve it algebraically, here's what the problem says. It says that y is equal to 5 minus 3x over 2. And if you think about, like, how do we find the inverses, we said let's take the x and the y's and let's actually swap their places. So if I swap their places, here's what's going to happen. We're going to have the x is now equal to 5 minus 3 y, and that's going to be divided by 2. So you can see from the original problem to the new one, we took the x and the y and we switched their places. So in order to get the new equation, we're going to go ahead and graph this. I'm sorry, we're going to solve this, okay? So we're going to solve for y. That means that this will be 2x is equal to 5 minus 3y. We're going to subtract 5. We get 2x minus 5 is equal to negative 3y. We're going to divide by negative 3. We get y is equal to 2x minus 5 over negative 3. That's supposed to be a 5 right there. Okay? And that is our inverse function. Okay, so we would actually conclude it by saying, instead of saying y equals, we would finalize and say that f of negative 1, the inverse, is equal to 2x minus 5 divided by negative 3. Now, let's take a look at the graph and see what this looks like. Okay, so for my first function here, we're going to have 5 minus 3x. So let me go to decimals here. Whoops. I'm going to start a new one. Okay. Let's start a new blank. And we're going to have y is equal to, I forgot what it was. What do we get? 5 minus 3x. So it's going to be divided by, and it's going to be 5 minus 3x over 2. So there's your first function. Now I'm going to show you what it looks like when we take y is equal to x and we reflect it. Okay, equal to x. This line, what we're going to do is we're going to make it a dotted line. And we're going to actually keep that there. Okay, and now here's our inverse function. We're going to take this picture and we're going to actually reflect it over. So the new function is going to be y is equal to, we said, let's see, 5 minus 2x over 3, right? 2x minus 5 over negative 3. 2x minus 5 over negative 3. Okay? And it actually reflected over. And again, when we're looking at this, you can easily just pick a point and check to see, do we have a reflection going on here? That we've got a point on this where we've got 2.50. That's on the green one right there. That's this point right here. Okay? So you can see that that point right there is at 2.50. Well, if we take that and reflect it, and we go up here, you'll see we have 0 and then 2.5. So those are points that actually just went ahead and just switched. Okay? All right. When we look at the domain and range for my original function, the domain for this, there's no restrictions on it. The only time we get restrictions is if there's a variable in the denominator or if this has a square root. So this goes from negative infinity to infinity. The range for this, when you look at the original picture, you can see it goes up and down forever. And so if we take those and we swap their places, we can see that the domain of the inverse and the range of the inverse is just swapped, and it's from negative infinity to infinity, and negative infinity, ran out of space, to infinity. Okay? And again, looking at that picture, you can see each graph goes left and right and up and down forever. Okay? Oops. All right, now let's take a look at another one here. Okay. So when we look at this one, okay, we have f of x is equal to 2x minus 5. And so when we look at this, let's actually review it just for the heck of it. Our parent function for this is a parabola. Okay, so if you recall, a parabola technically looks like this. So the changes that are going to take place here is, remember, we have to factor that 2 out, and we're going to be left with x minus 5 over 2 squared. So this tells us that our graph is going to shift to the right 5 over 2, and there's going to be a horizontal shrink by 1/2. Okay? So let's take a look here. When we look at the graph for this, because it's been shifted right and shrunk, and we look at this graph, we have to do a couple of tests. Okay? So when we look at this, it passes the horizontal line test, and it passes the vertical line test. So this has a one-to-one relationship on it. Okay? The graph of this, when we look at it, the domain of this goes left forever, and it goes to right forever. And the range of this is going to go from 0 to infinity. Okay, it goes left forever, goes right forever, it goes up forever, but it stops at 0. Well, looking at my new function here, the inverse function, the inverse domain is going to be from 0 to infinity, and my range, the inverse, is going to be from negative infinity to infinity. Okay, well, what's this going to look like, and how do we do this? Well, there's a lot of algebra here. Let's solve this. X is equal to 2y minus 5 squared. Okay, that's taking the x and the y and switching them. Let's resolve for x. So that means we're going to have the square root of x is equal to 2y minus 5. Now, because we took the square root, you have to remember that we get plus or minus here. Okay? If I add 5 to this, we're going to have 5 plus or minus the square root of x equals 2y. Divide by 2, we have 5 plus or minus the square root of x divided by 2 is equal to y. Now this is important. I'm going to give it to this in 1 second, but I want you to watch what happens when we do these graphs. Okay, so I'm going to change this one. And that first graph we said was going to be 5 plus the square root of x divided by 2. Okay. And then we've got 5 minus the square root of x, square root of x, divided by 2. See that it makes our parabola right there? And then the original function that was in this was we had 2x minus 5 squared. Okay, and you can see what ends up happening there is we have a reflection, pretty obvious the reflection, but what ends up happening is if you take a look at the value right here, you see this bottom value right here? Well, in the range of the first function, remember the range starts at 0 and goes up forever. Well, now the domain of this function is that it starts at 0 and it goes to the right forever. And that's what happened in here is that the domain and the range swapped places. Okay? All right, let's take a look at this one here. Bunch of stuff to look at here. All right, first off, and this is a doozy of one. I would probably put a star by this one because this one's kind of challenging. Okay? So a couple things you need to know. This right here, it generates a horizontal asymptote. You should remember that from honors algebra. So that means that y is equal to 2. So if we look at the graph of this, we've got y is equal to 2. We've got this horizontal line that's going through my picture. We have a domain restriction in this one. When we look at this, we know that 2x minus 3 cannot equal 0, because if we did, it would be undefined. So let me move me. I'm always in the way. We get x cannot equal 3 over 2. Okay, so at 3 over 2, we've got this restriction right here. And then let's go ahead and look at the domain and the range for this. So the domain of my original function here is that it can equal everything. It just cannot equal 3 over 2. Okay, so this is going to be our domain. The range for this, when we look at it, in this case, we're going to end up having a asymptote. I want you guys to see what this looks like here. So 4x plus 8. So we're going to have y is equal to 4x plus 8. And then over 2x minus 3. Okay, and this is what our graph looks like here. Okay, and so when you look out, I'm going to zoom out here. What I want you to really pay attention to is the fact that you can see in black here, the graph is really following a line, and its y is equal to 2. That's that horizontal asymptote that our graph follows. It doesn't really cross it, it just generally approaches it. And we'll talk more about horizontal asymptotes and what the definition is, but I just want you guys to see it in the picture. Okay, so I'm going to turn that off. All right, and our range for this, as you saw, the graph went up forever and down forever, but it never hit that 2. Okay, so this is our domain and range. Now what happens if we take and we swap the places? The inverse domain and the inverse range is going to be negative infinity to 2, and then from 2 to infinity, and negative infinity to 3 over 2, and 3 over 2 to infinity. Okay, now this is the hardest part, finding this equation. This is going to require a lot of algebra. Okay, so we get y is equal to 4x plus 8, and then 2x minus 3. What we're going to do is, remember, we're going to take the x and the y's, and we're going to actually replace them. We're going to swap them. So this is going to become a y and a y, and this will be an x now. So we have to try to solve for y again. Try to pause it and see if you can figure it out. Okay. I'm going to go ahead and continue. So to do this, you multiply both sides by 2y minus 3. Okay. What this will do is it will cancel out those denominators on the right side. We're going to be left with 2xy minus 3x is going to equal 4y plus 8. Now, if we're trying to solve for y, the issue we have is that there's 2 y's in this problem. So let's get those 2 y's together on one side. So we have 2xy minus 4y if I move the 4y over. And I'm going to take that 3x and move it over to the other side, and we're going to have 3x plus 8. I'm going to go ahead and factor out a y. The reason we do that is because I just turned 2 of those y's into now there's only 1 y in the problem. And if I divide both sides by that 2x minus 4, we have 3x plus 8 over 2x minus 4. And this is it. This is our new equation. Now look at what happened, okay? It happens every single time. The horizontal asymptote here is now 3 over 2. That's what we've got in our inverse right there. The domain restriction here, when we look at it, is that 2x minus 4 is going to end up equaling can't equal 0, which means that x cannot equal 2. And that's what we've got right here. So let's go back and graph this other function so we can see it in action. We've got y equals 3x plus 8. And that's going to be divided by 2x minus 4. They look very similar, but you can see there's a little reflection that takes place over that y equals x. All right, let's move on. So now how do we find inverses algebraically and prove them? Whenever it says verify, what we're asking to do is actually prove that these are in fact inverses. So the way we do that is not by switching x and y and solving. This is where we do composite functions. We take and we have to verify both f of g of x and g of f of x. So f of g of x, remember, is the way of saying, here's my function f of x, here's my function g of x. What happens when I take this function and put it into here? What does that look like? Well, we end up with 3, and then we're going to have x plus 7 over 3, and then minus 7. Okay, that's taking that g of x and plugging it in. And what's going to happen is our 3's cancel. We're left with x plus 7 minus 7. And we go ahead and simplify, we get x. That verifies it going to the one direction. Let's take and verify it the other direction, putting this in here. And what that will look like is, we did it again, that x plus 7, whoops, we're going to have that plus 7 over 3. And in place of that x, we're going to put a 3x minus 7. That's, again, coming from that left blue function there. If I take it, I simplify this now, we're going to have equals 3x over 3, which simply equals x. So this is that biconditional statement that we just proved. We just proved that when we do g of f of x, that equals x, and that when we do f of g of x, that also equals x. So we did that in both directions there, okay? That pretty much concludes inverses. I think that's it. I think you guys got this. I think you're gonna crush it. If you have any questions, please reach out. There might be a couple of questions that are challenging, but my go-to for this is just tell you, look at the domain and the range, okay? You take care of each other. Don't forget to like and subscribe to my YouTube channel. Have a wonderful day.